Hello everyone. So I'm going to go over the OS map, which we broke down into what you will be seeing in a couple of minutes. The reason why I'm recording this again in English is because there were some requests, plus uh, Mohan, who's working with me on this map, also requested that. So that's why I will be going over this map again, but this time in English. So the reason why me and I think a lot of other folks in cybersecurity and digital forensics and incident response believe operating system is a core for your understanding these fields is this map and all the ideas and the concepts that you will get to learn while studying operating system. So I'm going to go over uh, the ideas here and the concepts which are covered and try to map them with topics in cybersecurity and DFIR. So first thing, processes. Lots of stuff are related to processes, whether we are talking about exploitation, malware analysis, whether it's just cybersecurity in general and policies and let's say control access controls, all these kind of stuff. Threat hunting process is an important topic, and processes does get explained in a lot of details in the operating system course. So one of the important concepts there is the management, process management, how the operating system manages processes, and that we broke it down to processes, scheduling, states, threads, and synchronization. So process is the any program once it's while it's on disk, when it's loaded into memory, and then your processor starts executing the instructions of that program while from running from memory. That's when we call it a process. So we need to create the process. So that's why we have process creation, process termination. Those are very important concepts. You learn them also in operating systems, and they are very important for you whether you're doing threat hunting, monitoring, malware analysis, etc. Scheduling. Also, the idea of scheduling. Why do we need scheduling? Why does an operating system do scheduling, and how does it do that? Uh, that's also explained in operating system. Queues. Why do we need a queue? We study queues and data structures, and usually we will go. At least when I studied data structures, we had to program them without using any of the available today classes and all of the, I would say, available libraries. In the past, you'll have to do it from scratch. So we learned that, but we never got to map that with why am I learning a queue? Okay, the concept is good. Maybe they explain an example, but how is it used in our computers? That wasn't covered in those courses. So I'm not saying it's not covered in all data structure courses, but at least the ones I took, they didn't cover that. So we didn't get an idea why was queues really important. So queues, they are important because you'll have many processes. They arrive, they want to uh, be able to execute, so they'll have to stand in a queue, and then the queue, based on some scheduling algorithms, will be executing them. Context switching, when, for example, the system switches from one process to the other. Maybe a process needs, let's say, just an example, needs 1 minute to finish its processing, but the scheduler says, hey, I'm only going to give you let's say, 20 seconds. Then that means the system will need to, after the first 20 seconds finish, it will need to save the state of the process and then switch to another process by loading the state of that process. And that's what context switching is. So those ideas, the switching, saving the state, that's all explained in operating system. States, same thing. Each process has a state. like processes created, processes in standby, processes in let's say suspended processes. A process might be in IO. Each operating system might have its own different naming conventions for the states, but in general, you'll have like process creating, running, stopped, paused, or suspended, stuff like that. Threads. Nowadays, our computers have multi-cores, and they might also have multi-processors. So the idea is to take advantage of that and be able to run your process on those cores and processors. And what that means is each, let's say, your program could be divided into chunks. Each chunk or each, let's say, each task could be scheduled to run on a different core or processor, and that way we'll have multi-threading. So even threads and how they work, how do we program them, they are also explained in operating system. Synchronization is very important when we have, for example, two processes and they want to synchronize between each other. And synchronization is a very important topic, especially if think of it like this: if we have two processes, both of them want to write on the same file. So how do we control that? Because if one process opens a file for write and the other also opens the file for write, then it means whatever process A is going to write, probably process B is going to wipe with whatever they write. So we need to find a way to synchronize that and prevent one process from overwriting the data of the other process. So that's why synchronization is also explained in operating systems, and usually we go over mutex, semaphores, monitors, and those are all software synchronization methods. And then there is also the hardware synchronization methods. Mutex, for example, they are also used by malware, and usually they are used by a malware to make sure that only one copy, sorry, of the sample is installed on this computer. So usually they might use a mutex. Also, when we go over processes, there's shared memory. So I jumped over this. So IPC, interprocess communication. So interprocess communication, and which means how do these processes communicate with each other. So there is many ways. Three of the main ways are shared memory. So two processes, process A and process B, they they agree to share a specific memory location, and then they start passing data between them using that memory location. Message passing, they might just agree on some method to pass messages. So they might send signals to each other, send a message to each other. That's another method. But I'm just, by the way, explaining the concepts. I'm not going into very much details about these because they are covered in operating system. And finally, client server. So even the idea of client server, by the way, uh, that's covered in networking. That's true. It's a network related. That's true. So if you're doing network security, network forensics, network monitoring, you need to understand networking. And networking is, at least I would say, the basic core concepts is covered in operating system. So the idea of client server, we have two processes. One is a client and one is a server communicating with each other. That's covered in operating system. Using a socket, so client server might use a socket. So a socket could be defined. You can think of a socket as an object which is used for process-to-process communication, and that socket uses a port number and an IP address. But at the end, it doesn't mean that the two processes have to be on separate computers. They actually can be on the same computer, but at the end, that object which is used for communication is a socket, and it uses an IP address and a port number. Socket use protocols. Protocols, you have TCP, UDP, and others. So even those protocols and the language which those sockets communicate with, those are covered in operating systems. We don't go into the details like TCP/IP, UDP, and those kind of stuff. Those are explained in networking, but at least they are mentioned there, they are covered there, and we understand why are they used there. Finally, when we talk about client server, there's also another method, which is RPC, remote procedure call. So that's another way of, let's say you have a shelf full of functions, and then you have which is acting as a server, and you have a client which needs only to use some data found on, or some process found on one shelf. So it will do a remote procedure call, and that will kind of call a function to run it remotely, get the answer, and send it back to the client. System services. So at the end, our processes are separated into user processes and system services. At the end, the service is actually a process. So system services are those which are usually running in kernel mode. If we go into separations and the mode, so we have user mode and kernel mode. You can think of a system service like the network discovery, uh, let's say, system. So once your computer comes up, there's a system or a service which is running. It will automatically, let's say, go do the network discovery and connect your device to the network. So those are system services, and they are running in, like I said, in kernel mode. And usually system services, a user does not kind of interact with them directly. You need like a middleware to interact with them. If we go also on operating system memory, when we go, memory is very important, whether you're doing memory forensics, whether you're doing exploitation, whether you're doing malware analysis, whether you're doing monitoring, all of kind of stuff. Actually, memory is very important. And when we go there, we understand addressing. What do we mean by logical addresses, physical addresses? What's the difference between them? What type of addresses are we actually dealing with? All those are explained in operating system. Also, memory management, it's a very important topic. So how to load, for example, an executable, or how to load a library. That details, so loading and unloading, or swapping in, swapping out. That's what we'll explain in a minute, in a couple of minutes. Those are also explained in operating system. Shared libraries also. We shared libraries, actually, even the static libraries. What's the difference between them? Those are also explained into operating systems, and we see why shared library is very important, especially if, let's say, you have 10 processes, all of them are using the same exact library. Then this means if we don't share that library, each one of those processes will have to load that library into the memory, and that's a waste of memory. So shared libraries is very useful in terms of optimizing the memory usage. Paging and page tables. So now your library is shared, and let's excuse me. Now your, let's say, let me explain two concepts. So now your executable wants to execute. Your executable is also divided, will be divided into something called a page, and a page has a static uh, size. So your executable might not be fully loaded into memory. I'll give you, maybe, if you look at some executables, their size is very big, maybe, so they will not be completely loaded in memory. What will happen is a chunk of that executable is actually loaded into memory, and when the system needs to run or execute another instruction which is not currently in memory, what will happen is it will do a page fault. It will go load the page into memory and then execute it. That's why we'll need page tables. So the page tables is kind of a way to index and have an idea which page is loaded, which page is not. If it's loaded, the, let's say, the system will automatically go to that page and execute whatever is in there, or load the data which is in there. If it's not loaded, it will, like I said, it will do a page fault, go load the library and update the page table. Same thing happens for a library. Just now we are talking about a library instead of a process. Swapping, even the idea of swapping. So when we talk about swapping is, let's say your process is now in memory. and then another process comes in. Let's say maybe it has a higher privilege over what the current process is running, and then it needs to run. So what will happen is the system will say, "Hey, I'm going to swap you out." So it will swap the lower privileged process out, and then it will swap in the process with the higher privilege. Just an example, by the way, that's not just what swapping is about. You can also think of, let's say, you want to swap in a page and you don't have space for it, so you'll swap out and swap in. All of those concepts are also explained in operating system, and they are very important, especially, for example, if you do memory forensics. Why, if you like dump the memory, why might you won't find everything in memory? The reason is probably the process is running, but not all of its part is in memory currently. Probably they are swapped out. Memory, virtual memory, the idea of virtual memory, we understand that in operating system. Page replacements, which page shall I replace? So uh, these are algorithms, and they explain which page should be replaced. Is it the least frequently used, or is it the most frequently used? That's maybe not a good idea, but those are different mechanisms which usually are explained also in operating systems. And also that shows you how important is when you study algorithms, uh, they will be used in operating systems. Compression, so memory could be compressed, or your code or whatever data is loaded could be compressed. There is a penalty for that, but at the end, memory does also provide that feature. So memory management and that kind of topic is also explained while studying operating systems. System calls, so you have a program running in user mode, and now it needs to do some, let's say it just needs to write to a file. So even when it needs to write to a file, that means if you open, let's say, Notepad, and you start typing, and then let's say that whatever you typed, you want to save it, then what that means is you need to save that on disk, and the only way to reach the disk is through the kernel. So in order to trigger the kernel to do that for you, you'll need to perform some kind of system call. So those are also very important, and you'll go in much more details. How important are they, the different system calls available on operating systems, and why are they used? Storage, very important if you do forensics. So storage is divided maybe into hard disk drive. Very important to understand what are hard disks, how they are managed, the management of hard disks, partitioning. When I partition a hard disk, how does that structure look like? Those we do them in usually in file system forensics, or even in an introductory forensic class. Volumes. So you have a hard disk, you split that hard disk into two partitions, and now that partition, you want to create a volume on the partition. So there are also different types of volumes. They are explained in operating systems. Also, when you format that partition or that volume, when you format it and now you create a file system, those are explained also in operating system. Blocks or clusters, regardless, that concept is also explained in operating system, and it's very important for anyone doing actually digital forensics. Volatile memory and non-volatile memory are very important, and you see them in operating system. At least we don't go, let's say, into every single one of them into very uh, I would say, into a lot of very much details. It depends, but at least you understand the types of volatile and non-volatile memory. They are important for you, especially if you do forensics, because let's say you have a case, you want to do IR, I mean incident response, and you need to acquire some evidence or some data. Then you'll need to know which ones are volatile, which are non-volatile, and that will help you understand which data should I start with. Virtual machines, even that concept is explained in operating systems, like what's a hypervisor, what's an emulator, what's a paravirtualization. Also, the difference between each one of them is actually explained in operating systems. Linkers and loaders, usually I remember I had them in one of my introductory, I think, to C++. Uh, they explained what a linker and loader, but not too much. So in operating systems, you'll see how they are important and how they will make a difference when you link a file, when you link libraries and you at compile time and all those kinds of stuff. So what's dynamic linking and all these kind of stuff, uh, those will be explained also in operating systems. Interfaces, whether CLI or GUI, or maybe there are other interfaces, those are also explained in operating systems. System architecture, there is a course for system architecture, that's true, but at least you learn the basics, like what's a single processor and how did our computers in the past, even though it had a single processor, which means one process at a time is one process at any specific time is running, still the idea of context switching helped achieve running multiple processes at the same time. Multiprocessors and why do we need them, and like explain the difference between them and between a single processor. We even go into, for example, the I forgot the I forgot the name, the terminology for it, but like for example, if you have a thread and you loaded the thread onto one processor, and or I think it's called process affinity, and you want that thread not to be, so if it does a context switch, you don't want that thread to be loaded onto another core, because probably the data which is going to be needed is already in the cache, which is currently near another core. So even those details, we explain them in operating systems. If we go to security, even security is explained in operating system. There is a course for all of these, that's true, but also the main concepts are explained in operating system. So you'll understand what do we mean by threat modeling. How do you model like your case, the scenario, or whatever you're trying to protect? How do you create a module for that, and then you see how can you protect it? What are the weak points that you have, and then that gives you a better idea into it gives you a better idea of how to apply some protection methods for that specific uh, for that specific scenario that you have. Policies and procedures also, even though we are talking about operating systems, uh, in general, you'll also have an idea of what to mean by policies, what do you mean by procedures, how does an operating system apply them. Maybe you can configure them on some systems. All those kind of stuff are also explained in operating systems. So when we go threat model, I divided it system, network, encryption, authentication. So systems, we'll explain access controls, we'll explain the rings and domains. So we'll explain access controls and the different kinds of access controls, like discretionary access control, role-based access control, uh, mandatory-based access control. I think it's mandatory based access control. I hope I didn't forget. Anyway, and I already said role based. So the other RBAC system is actually a rule based access control, and other types of controls could be through sandboxing. So you might be running your application process system in a sandbox. You might be doing syscall filtering. So you might be monitoring whatever syscalls is be system calls is being required, and you filter them. So if they are allowed, you allow them to go through. If they are not allowed, you interrupt them. Rings like ring 0, ring 1, ring 2, those kind of, let's say, separations. And why do we need them? To provide some kind of privileges or separations between each layer, and each layer might have more control over the system than the upper layer. Domains, you might be even dividing your system into, so there might be a set of processes running in domains, and then you define the communications between that domain. Networking, again, we also explain that in operating systems, networking, and all those are very important, regardless, network security, network monitoring, network forensics. All of those are important. And actually, even the access controls, I forgot to mention that those are important, whether you're doing auditing, whether you're doing hardening your system. All of those are important to understand, and we do cover them in operating system. If we go to encryption, I know there's usually a course for cryptography, but at least even in operating system, you get to understand that there are some encryption algorithms used, for example, such as TLS, AES, REDIS, RSA, etc. Some might be used for data while in transmission. Some might be used, they are good for data while in storage, etc. All of those are also explained kind of in operating system. Authentication, so basic types of authentication, maybe like password and biometrics, or maybe even tokens. I didn't add that one, like a hardware token. So those are also explained in operating system, at least the main concept of them. You don't dig into them, but at least you do get to have an idea about them in operating system. Finally, based on the map which I have, is file systems, and file systems are very important if you are going to do forensics, and especially, for example, file system forensics. So we'll understand the basic idea of a file, like what types of files do we have. We basically have two types. We have a text file and we have a binary file. A text file just includes text, and a binary file will usually have a structure. At least I like to call it that way. So we'll also understand those in operating systems. We'll understand the operations, like read, write, open, close, go to the end of the file, go to the cursor, move the cursor to the end of the file, move the cursor to the beginning of the file, move it like to an offset. All of those are very important topics which are explained in operating system. Attributes, the different kinds of attributes which a file might have, like if it's an archive file, if it's a system file, if it's hidden, all those kind of files. Attributes are also explained in operating systems. Structure, if a file has a structure, usually at least basics files and their structures, they also get explained in operating system. Allocation methods, file system allocation methods. So how do I allocate files? So you want to write a file to disk. How are you going to allocate that file? Is it contiguous, or is it using like a linked list, or is it based on some indexing? Those different types of allocation methods are also explained in operating system. So now you've allocated a file. How do you access that file? Is it going sequentially? When I mean sequentially, I mean maybe the cursor starts at the beginning of the disk and then all starts sequentially searching for the file until it finds it. That's one way, but it's not the best way. Or is it direct access, like you directly go, you know where the file is, and you go and allocate the, you go, I'm sorry, and you call that file. Directory structures. So even the directory structures, like at least the basics of them, a directory is a type of file, but at the end, the directory will have other files in it. So it has actually entries for files. So it's a file, but it has entries for files. So it's just a special type of file. That directory structure, how it's represented in file systems, also are explained in operating systems. Types of file systems, so you'll get to understand different types of file systems. Like usually most of the operating system books will even reflect on, let's say, FAT32, NTFS, or ext4. So they will kind of map what they explain in the book with these real life scenario operating systems. So the types and their structures, if it's a virtual, and the types and their structures are explained. They might not be explained in details because at the end there are they explain the concepts and they do go into a lot of details, but maybe not into those FAT32 NTFS kind of specific file system details. Also, mounting a file system and unmounting a file system, what does that mean? By adding the file system to your tree? Is it a separate tree? Is it like on Windows, each file system is mounted to a separate drive letter? All the idea of mounting and unmounting, if it was mounted successfully, if it wasn't mounted successfully, what happens there? All that is explained in operating system. Virtual file systems also explained in operating system. At least you'll get an idea of what that is. And finally, distributed file systems are also explained in operating systems. I'll give you at least just one example, like HDFS, Hadoop file system. It could be considered, it is a distributed file system. So you have a main server. That main server is attached to many client servers or storage servers, and or let's call it that way. And so when you want to store a file, if it's a big file or if it's a small file, depending on some settings and configuration, that file might get distributed either evenly or not even in different kind of sizes across those clients, so those storage devices. And you might even have replications of that. And then when someone needs that file, they talk or they communicate with the main server, and the main server knows where the file is, and it goes communicates with the clients, and then calls the clients, and it retrieves back that file for you. All those kind of details are all explained in operating systems. So as you can see, OS is a really important topic. This is not a complete map, by the way. There is a one being updated. We are kind of updating it as we go, but at least this does give you a general idea of why operating system is important and why we highly recommend you study operating system, whether you're doing cybersecurity or digital forensics, doing threat hunting, malware analysis, exploitation, monitoring, auditing, all of those kind of job positions. It's really good to have an OS background in there. That's all for this video. I hope it was useful, and yeah, have a good day. Bye.